Thank you. All right, so I'll be talking about a quantum algorithm for simulating the time evolution of lattice Hamiltonians. If you don't know what any of that means, that's okay. I'm going to explain everything. I don't assume that people in this audience have a background in quantum computing. And because of that, maybe there won't be so much meat in this talk for the experts, but I'll make side comments for the experts. So throughout the talk, if you don't understand anything, that was probably meant for the experts, and like the talk is structured in such a way that you'll still understand the remainder of the talk, maybe except like the last 2 slides or so. Okay, so this work is joint work with Jungwon Ha, Matt Hastings, and Guanghao Lo, who are all at Microsoft Research in Redmond with me. All right, so let me start with a 1-slide quick summary of what this talk is about. We give a new quantum algorithm for this problem of simulating the time evolution of a lattice Hamiltonian. And we also prove a matching lower bound that up to log factors, essentially no quantum algorithm can do better than our algorithm in the sense that it cannot use fewer gates. And this is an unconditional lower bound, doesn't make any complexity theoretic assumptions. Okay, so what is the problem we're trying to solve? It's the problem of simulating a physical system. And I don't want to be pretentious, but the problem starts like a long, long time ago. And in fact, even the study of this problem has, it's been studied for a very long time. And I'd say the problem, let's say the specific problem of just understanding how planetary bodies move was understood, let's say, 400 years ago by Kepler. So finally, like people thought about this and people had incorrect ideas of how this worked. And then sometime in the 1600s, Kepler figured out how planetary bodies move. And what we mean by he figured out, or like he had an understanding of the system, I mean is that he was able to predict the motion of these planetary bodies. So that's one like operational interpretation of what it means when you say you understand a physical theory, or like you say that we understand how electrons, whatever. What it means is now you can predict how these things will behave in nature. So if you're able to predict the behavior of nature, that's one way of saying that you really understand what's going on. And like this is essentially what physics studies, right? It has been studying for like hundreds of years. How do we understand nature itself? How do things change with time? And there's a very obvious computational question here, which is just because you understand how things, how nature evolves in time, or like what will happen if you do a certain object, certain thing in the real world, doesn't mean you can predict this computationally efficiently. Like, can you predict the behavior of systems in polynomial time, in a time-efficient manner? Presumably Kepler had a polynomial time algorithm because he was actually able to predict the motion of bodies. And we're going to ask the same question, but now not for classical systems like this, but for quantum systems. So, for example, you put some atoms together. The question might be what's going to happen in time? Like how are these atoms going to interact with each other? Are they going to combine to form a molecule? Or is something else going to happen? Are they going to repel? So this is the kind of problem we're talking about, simulating physics. And the general description of the problem is something like this. You have a description of the physical system, and by this I mean like the laws that govern time evolution, the laws of physics that tell you how the constituent particles in your system interact with each other. And I'll tell you the initial state, like I'll tell you what things look like right now. And your computational problem is to figure out what the system will look like after time t. So t is the input is t, the time. You're also allowed to make some error, so there'll be some error parameter epsilon. And you're given the laws, and you're given the initial state. So this is like a general description of this problem. And like here's a quick example. Like maybe somebody's dropping a ball, and I'll give you the position and velocity of the ball, and then you have to predict where the ball will be after time t. Like this is a simple problem that you might have had to solve in high school. It's easy to do. You can do it in polynomial time. So we want to solve this problem, but not for classical systems like this, but for quantum systems. And the general problem is the same, as I said before. That's the template. And we want to take this template and make it specific to quantum systems. And what does that mean? We'll have to define what a quantum initial state, final state, and what are the laws that govern a quantum system. And the way to generalize this is you have an initial state, which is often called the wave function of the system. And because we're computer scientists and we like discrete things, we're just going to think of this as a discrete vector of some fixed length. The final state is also similarly a vector, and the object that encodes the laws that govern the system is called the Hamiltonian H. And I'll say a little more about what this Hamiltonian is, but this is essentially the setup. So you're given the initial state of the system, you're given this Hamiltonian that tells you how particles interact with each other, and you have to figure out what the final state will be after time t. So this is the computational problem. And The mathematical solution to this problem is known. Like, this is what Schrodinger's equation tells us in quantum mechanics. It tells us how the final state relates to the initial state and the Hamiltonian. And the solution to the Schrodinger equation is this over here. So what it says is, so if you're not familiar with quantum notation, this is a vector. H is a matrix, so the exponential of a matrix is also a matrix. So this is a matrix, this is a vector. And Schrodinger's equation tells us that if you take the initial vector and the matrix that tells you how the vector changes with time, you'll get the final vector, the state of the system. And to be a little more concrete, this is going to be a vector of length 2 to the n. This is going to be a matrix of size 2 to the n by 2 to the n. And this is going to be a vector of length 2 to the n, so this is matrix vector multiplication. And the reason you have 2 to the n is I want to think of n as being the number of particles in the system, like the number of, like in a problem with like planets or something, it's like the number of objects. But here, I'm going to think of these individual constituent particles as just being quantum bits or qubits, and that's where the 2 comes from. So we have like a quantum bit that can be either 0 or 1, but unlike a classical bit that can be only 0 or 1, this is a quantum bit, so it can be a superposition of 0 and 1. So, but it still has 2 possible states, and that's where the 2 is coming from. So if you have n qubits, you need a vector of length 2 to the n to talk about it. So your initial state is some vector of length 2 to the n. You're given a description of the Hamiltonian, which governs how the system will change with time, and you've got to figure out this final guy over here. All right, so that's the problem of simulating the behavior of a quantum system. This is often called the Hamiltonian simulation problem. You might have heard this phrase before. There have been a couple of talks on this topic at Stock and Fox in the last couple of years. And maybe let me just say one thing before I go on. If you take one thing away from this talk, you should take away that this problem, the problem of simulating a real quantum mechanical system, is solvable on a quantum computer for very general classes of Hamiltonians. So for Hamiltonians that actually arise in practice, so things that describe real physical systems that you might care about, like systems in chemistry or material science, condensed matter physics, et cetera, all of these problems can be solved in polynomial time on a quantum computer. So that's one thing I just want to get across. And the complexity class of problems that can be solved on a quantum computer is technically called BQP, which stands for bounded error quantum polynomial time. Okay, so that's some background on this problem, of this very general problem of just simulating physics on a computer. So let me say a little more formally what the problem actually is. So as I said before, the thing we want to do is, we want to solve this problem. Essentially, you're given the initial state, and you want to implement this map. So a formal version of this is going to be, you're given this Hamiltonian H, which I said before is a 2 to the n by 2 to the n. It's actually a Hermitian matrix. And you want to implement this operator, e to the minus iht, so by means of a quantum circuit. So if you have a quantum circuit that implements this operator, you can just plug in any initial state you feel like to the circuit, and then the circuit will evaluate what the final state is. So the goal is just to implement this unitary e to the minus iht. As I said before, H is a 2 to the n by 2 to the n Hermitian matrix, and it turns out if you exponentiate a Hermitian matrix in this way, you will get a unitary. And so it's something that can actually be represented by a quantum circuit. But that's the basic problem. I'll give you this Hamiltonian, time t, epsilon, and you have to come up with a quantum circuit which approximates this operator e to the minus iht. Now, this isn't a fully formal specification of the problem because I haven't told you how the Hamiltonian is represented. Because as I said, it's an exponentially large object. We don't just want to write it down on a piece of paper because that would be the input size would then be 2 to the n. And we want to solve this problem in polynomial time. And by polynomial time, I mean poly n, where n is like the number of particles in the system. That's kind of the natural size parameter. That if you want to simulate the behavior of n particles interacting with each other, you roughly want to take polynomial in n time, not polynomial in 2 to the n time. So to formalize this problem, I'll have to explain how this Hamiltonian is specified. I won't do that right now. And the classes of Hamiltonians that we study in real life usually will give you a natural, succinct specification of the Hamiltonian in polynomial size. But I'll defer that for the moment. So everything that I've said so far maybe kind of obviously motivates why we should be studying this problem, because, well, it's an interesting, basic, fundamental problem in physics. You want to be able to do physics computationally efficiently, predict things in polynomial time. And in fact, there's more motivations. In fact, it's one of the best applications of quantum computing. So I don't know if you guys have been keeping up with the news, but there's a whole host of government and industry efforts right now to make quantum computers, and with companies all over the world, including Microsoft and IBM, Google, et cetera, trying to make quantum computers. And if you ask them, like, why are you making quantum computers? What are you going to do with it? One of the main applications is going to be simulating physical systems. People might have different ideas of which physical systems they want to simulate. Some people want to do chemistry, and some people want to do some condensed matter systems, or maybe even material science, pharmaceuticals, I don't know. But this is usually the main application that anyone will say for what we'll do once we have full-scale general-purpose quantum computers. And in fact, this was the original application proposed by Feynman, like back in the day when he proposed that we should study quantum computation. He said, this is something we would like to do. And in fact, this is a great application of commercial interest because currently a significant fraction of the world's computational power, like if you look at logs of supercomputers around the world and what they're spending their time doing, they're actually solving special cases of this problem. So it's actually a useful problem commercially and also like for fundamental physics and so on. So it's just a useful problem all around. It's also useful for algorithm designers such as myself because you can use this problem as a subroutine in designing other quantum algorithms, and this has been done in the past, and there's a whole host of interesting quantum algorithms such as the quantum algorithm for solving a linear system of equations, which uses Hamiltonian simulation as a subroutine. So there's a bunch of reasons to study that. And finally, I just wanted to say that this problem is BQP complete, and what I mean by that is it can be solved by a quantum computer, but it's also one of the hardest problems that can be solved by a quantum computer. And this isn't a very deep statement. It's kind of just saying the problem of simulating quantum mechanics is one of the hardest things you can do on a quantum computer because the problem of simulating a quantum computer itself is a problem of simulating quantum mechanics. So, if you could simulate arbitrary quantum systems on your classical machine, then you can also simulate a quantum computer. So that's why it's BQP complete. So we don't expect that to be a classical algorithm. Otherwise, there will be classical algorithms for everything quantum computers can do, including factoring and so on. Okay, so that's all I wanted to say about this general problem. Let me get a little more specific about the class of Hamiltonians that we deal with. And the problem that we deal with is this class of Hamiltonians called geometrically local or specifically lattice Hamiltonians. And this is what a geometrically local Hamiltonian is. It's a Hamiltonian in qubits that can be written in the following format. H can be written as a sum of hj's, where each hj only acts on a constant number of qubits at a time. And this constant number of qubits, let's say there's 3 of them at a time, they're adjacent. And I've highlighted the word adjacent and geometrically to enforce the idea that adjacent only makes sense once you have a geometry. So you want to think of these qubits as being laid out in space somewhere. Like maybe they're on a line, and every term in the Hamiltonian only has 3 of them next to each other, interacting with each other. And this class of Hamiltonians has an obvious polynomial size specification, which is you tell me each of these hj's. There can at most be a polynomial number of different hj's because each hj only interacts a constant number of qubits, let's say 3 of them at a time. And each hj is just a constant sized object because it's only about constant many qubits. So you specify each of these hj's, and now you've specified all of h. So you've implicitly specified an exponentially large operator by just specifying these tiny constant sized things.
Up to error.
Sorry?
Up to error because each of these are complex numbers.
Oh, sure, that's true. Okay, yeah, so I guess in principle these could be complex numbers, and we will just approximate them to some precision. But that's going to be okay because we want our final answer also to be correct only to some epsilon. So we don't mind making tiny approximations in the input. And the specific class of Hamiltonians that we're going to talk about are lattice Hamiltonians, which are Hamiltonians that you can embed on a grid. So, for example, on the line or on a 2D grid or 3D grid. And this sounds like a very specific class of Hamiltonians, but actually it encompasses essentially everything in physics. In some kind of strict interpretation, every physical system has to be embeddable in this kind of Hamiltonian, and if it weren't, it would like violate special relativity and so on. But suffice it to say that this is a very general class of Hamiltonians that people actually care about. So it's not a significant restriction to study these. And let me just give you a pictorial example of one such Hamiltonian. You have like these n qubits on a line, and each individual term hj only interacts qubits that are close to each other. So this one has 1, 2, 3, and this guy has 2, 3, 4, and so on. All right, so this is a setup of the problem. And there are a couple of known algorithms for Hamiltonian simulation in general, and we could try to apply them to this specific problem. And one thing we could do is there's been a long list of works on Hamiltonian simulation algorithms that are query optimal. So I haven't told you what that means, but previous works in Hamiltonian simulation have often considered the Hamiltonian H, which is this exponentially large object, as being available through a black box. So you just query it and ask it for entries, and it'll reply with something. So you just think of there being a black box that knows the Hamiltonian. So now you don't have to worry about the specification of the Hamiltonian. And in that framework, there are algorithms that are optimal in terms of the number of queries they make to the algorithm. they have complexity that roughly goes like this, which is the number of qubits times the time that you want to evolve the system for times some log factors. The problem is when you take this algorithm and actually get a circuit out of this, you have to take this black box for this Hamiltonian H and make it, you have to white box it. You have to come up with an actual circuit that implements this. And this query oracle needs something like order n gates to implement. And so this is going to blow up your gate complexity n squared times t, times log factors. And this is a bit of a problem. This was also observed in a recent paper of Andrew Childs et al., where they went through this exercise of taking the current known algorithms and running them against a very simple lattice Hamiltonian, and they observed that all of them go like this. There's another previous work that could be applied to this situation, which is an algorithm of Jordan, Lee, and Preskel from 2014. We weren't actually aware of this work when we started this, and this work has complexity that's slightly superlinear in n and t, but the bad part is that its epsilon scaling just got significantly worse. Now it's a polynomial in 1 over epsilon as opposed to log 1 over epsilon over here. So we weren't aware of this work, and actually it's not totally clear that the algorithm presented in the papers is rigorous. We think it can be made to work rigorously, but there's some more work needed. So, all right, so I can now present our results. So what we do is we achieve the best of both worlds. So we achieve an algorithm whose complexity is n times t times some log factors. So we show any lattice Hamiltonian can be simulated with this complexity. And specifically, in this number of 2-qubit gates, and the gates that we use will also respect the geometry of the Hamiltonian. This is not often a requirement in quantum circuits. You're usually allowed to use quantum circuits that can have gates that are non-local. You can have one 2-qubit gate that has qubit number 1 and qubit number n talking to each other, but our algorithm will always produce circuits that have geometrically local gates, so that's kind of nice. And our algorithm also extends to time-dependent Hamiltonians, which I haven't defined at all, but it's really easy to define what they are. It's just the Hamiltonian is a matrix. A time-dependent Hamiltonian is a matrix where every entry of the Hamiltonian is now a function of time. Okay, so that's not very complicated, but we need some more restrictions on this function. This function cannot vary arbitrarily, and we impose some very reasonable restrictions, like for one, it needs to be efficiently computable, so you need to have an algorithm that can tell you what the entry is at any given time. And it should be piecewise slowly varying. And what we mean by that, it should be a sum of pieces, and within each piece, it should vary slowly, as in its derivative should be a constant. So these are very mild assumptions and capture a pretty reasonable class of Hamiltonians, of time-dependent Hamiltonians that you might like. So that's our main algorithmic result. And we show a matching lower bound, which is that for any n and t up to some exponential, there is a piecewise constant Hamiltonian or a slowly varying Hamiltonian. It's your choice. That's, in fact, a one-dimensional Hamiltonian, so just the qubits are laid out on a line, such that any quantum circuit that approximates this operation needs order n times t gates. So up to log factors, that's a matching lower bound in n and t. And our lower bound holds against a very strong class of circuits. So the class of circuits itself is allowed to use an unlimited number of extra qubits and can use arbitrary 2-qubit non-local gates. It can even use them from like an uncountable gate set, like from the full continuum of gates. Like it doesn't have to be from a discrete gate set. And finally, our lower bound also holds if we only care about the output state on 1 qubit. So in the traditional problem, you're supposed to output the final state of all n qubits, but sometimes you only need the state of 1 qubit. Maybe you're going to do something with that particular piece of information. We show that the lower bound still holds in this case. So even in this very weak simulation model, you still have to use as many resources as our algorithm does, but our algorithm, of course, gets you the full answer right. So that's a very strong lower bound. And in the last couple of minutes, let me give you just an idea of one technique that we use in our algorithm. This might be a little technical. Hopefully, you'll get something from this. The main technical component in our algorithm is something called a Lieb-Robinson bound. This is a technique from mathematical physics. And it's a theorem that says that in a system that evolves under a geometrically local Hamiltonian, information can only travel at a constant speed. So there's a lot of physicsy terms over here that don't necessarily mean anything. So let me just give you an example of a system where it's kind of obvious that information travels at a constant speed, and maybe that might help you get some intuition for what I mean. Is just think of a quantum circuit where you have geometrically local gates. So something like this. So you have n qubits, and these are gates that act on 2 qubits at a time. And the thing that's easy to observe is that the output state over here, these 3 qubits, will have nothing to do with the first 6 qubits or the gates in black, because you see there's a line across here that no gate crosses that line. So everything over here doesn't care about what's going on over here or going on over here. So in that sense, these qubits, as time progresses, can only affect things that are constant distance away, and they depend linearly on time. So, So this is obviously true for a unitary circuit like this. It's not obviously true for a geometrically local Hamiltonian. In fact, it's strictly false. Like, you can affect things that are very far away, but only with exponentially small weight. So this Lieb-Robinson bound is a beautiful theorem that formalizes this connection and says that essentially, if you're evolving under this geometrically local Hamiltonian, stuff can only influence other qubits linearly far away. And there's a formal statement, but maybe I won't get into that because I'm kind of running low on time and it's very technical. But yeah, essentially just says that any quantum operator supported on some qubits over here doesn't care about whether you time evolve with the entire Hamiltonian everywhere or just with the Hamiltonian on this purple region over here, because everything else is so far away it kind of doesn't know the difference between these two objects. So that's kind of the key technical tool that we use. And then applying this tool, what we're able to do is we're able to take our Hamiltonian simulation problem, which is on n qubits, and break it up into a product of 3 smaller simulation problems. And we show that the error induced in this breaking up is small because of this aforementioned Lieb-Robinson bound. And then we keep doing this over and over again, and you'll break it up into smaller pieces, and you keep breaking it up into smaller pieces. And finally, you break up your entire Hamiltonian simulation into a bunch of very tiny pieces. Each piece is only logarithmically sized. And on this tiny piece, you can use any old Hamiltonian simulation algorithm from before to do it. So our main contribution is to use these Lieb-Robinson bounds and take this large problem and break it up into tiny problems. And for this tiny problem, you can use any of the known algorithms, except there's a caveat. These algorithms should also have very good dependence on epsilon. They should go like log 1 or epsilon as opposed to polynomial in 1 or epsilon. But we have many algorithms like that, so that's not an issue. And that's basically an overview of how our algorithm works. We take this big problem, break it up into little pieces using this tool from mathematical physics, then use any non-Hamiltonian simulation algorithm. And that's about it. I'll conclude by saying this was the results I presented. We have this new algorithm, uses roughly n times t times log factor number of gates. That's optimal. We have a matching lower bound. Lower bound even holds if we only care about the output state on 1 qubit. We leave open some interesting open problems about sparse Hamiltonian simulation in general. Can you have like a best of all worlds kind of Hamiltonian simulation algorithm in the query model, which I didn't actually introduce, so I'll just leave it up there for experts. There's a few other problems about, can you do interesting simulation if you're promised that you lie in the low energy subspace of the system? Most of these are kind of technical problems directed towards experts, so I'll just leave it up here if people want to read this. And that's all I wanted to say. Thanks. The upper bound holds in any dimension d. And in fact, if you naively apply the results, you'll get an exponential scaling with d, which is not too bad because for most physical systems, d will be at most 3, because we live in a 3-dimensional world and all that stuff. But we also give an improved algorithm that now has polynomial scaling with d, so you can even go to polynomially large dimensions. Any other questions?
Can you say a word on the lower bound?
Oh, so how is the lower bound proved? Yeah, that's an interesting question because it's a lower bound on the number of gates, which are very hard to come by because for example, we cannot even prove that 3-sat needs a superlinear number of gates. And so what's going on over here is we prove a circuit size hierarchy theorem for quantum circuits. That's the first step that shows that essentially there's a problem that a quantum circuit of size s can solve, but no quantum circuit of size s over log s or something can solve. This is easy to prove even classically. Right? And then the circuit size hierarchy theorem in itself is not sufficient because that would just be an apples to apples comparison. Like it would take one class of quantum circuits and show that giving it more resources allows it to do more stuff. But here we're comparing 2 different kinds of objects. We're comparing evolution to geometrically local Hamiltonians on the one hand versus a very strong class of quantum circuits on the other hand, where we allow the quantum circuits to use unlimited ancillas and to use non-local quantum gates and so on. So we're giving one side more power, but essentially it's still a hierarchy theorem, but just the 2 things that are being compared are of different powers. So we prove a circuit size hierarchy theorem, but on the one side, on the side that gets more resources, like that gets more size, we enforce stronger constraints. It has to be geometrically local. And on the weaker side, we give more stuff, but you're still able to prove a hierarchy theorem. And that's how you get it.